Hello, we're back. We're back for day 3 of language dev. I don't have much time. I'll probably just stream for an hour. Pretty tired. Couldn't sleep well last night, but try and do something. Just see if the stream is working. Yeah, okay, we got it. Cool. So, what I want to do today, I don't really feel like fleshing out the recursive descent. We'll need to do that. I got curious about relearning how to make a Pratt Parser, which is similar to what we were doing yesterday. It's just another form of recursive descent. It can be faster because you don't need to construct a whole tree-like structure to parse the expression. And I guess we'll just jump into it. It's an alternative to recursive descent. It's still recursive. You still use precedence. I'll just show you how to put it together, and then you can play around with it. But I think ultimately we're going to keep working with recursive descent for now. Just adding an extra clause because I forgot to do that yesterday. So as a quick review, where even is our recursive descent stuff? So we go through, well, this is when we're evaluating it. We call expression, which calls equality, which calls comparison, etc., etc. You make some binary expressions, and you go all the way down to primary, which collapses all the way back up, right? And so we're going to do a similar idea. This generates expression pointers, and so they point to more and more pointers until you have the full expression generated. It's called an abstract syntax tree, and we can just do an alternative design for it where we're going to have precedence tokens or an enumerator for precedence. So type def enum, we'll just call it prec type, short for precedence type. And then we'll have prec none. We'll go all the way back up, starting from lower precedence to higher precedence. We'll have equality, or I guess I should put an assign. Assignment goes before equality. Comparison, I'll just call it comp. Term, factor, unary. You can add call in there if we want. We're not really going to use it. And then finally primary. Call is for functions, just so you're aware. Don't really need those comments. So those are the different precedences. And now using that, we're going to make a new struct. I'm going to call it parse rule. Parser rule, yeah, why not? And this will contain precedence type, or rather, we need one for every token, so we can just call it precedence type prec. We'll have token type, or t-type, I don't really know, it doesn't really matter. And then we're going to need function calls, or function pointers. And so they're both going to return expression pointers. We're going to have a prefix. I think this is how you do it. Or, is that it? Prefix, which takes nothing. And then the infix, which needs to take an expression. So this compiles, cool. Okay, this is how you do function pointers in C. You know, you can just as easily do, like for a function that doesn't return anything, you can do like a null func, I don't know, you can call it whatever you want. And that still compiles, and then you can set it to something like void, like that, right? But we don't need that. And so now using the struct, we can make an array of parse rules. Parse rule rules, we'll just leave it empty and slowly fill it up. And so here we will just copy over every single token that we've defined so far, and we'll generate a rule for it. Like that. It's going to get messy. Okay. So those are the tokens. These are going to be the function pointers. And then we're going to have the precedence, which we can assign to none. There we go. A big array of all the tokens that we have so far. Get rid of this 0 thing. I guess we can straighten it out, because we're going to want to drop in some functions that we make. If you're curious about how all this works, you can reference chapter 17 from Crafting Interpreters. I'm mimicking that design, but instead of I can explain it in a second. He uses a stack-based virtual machine. We're using a register-based virtual machine, and we want to make it easier to debug, so I mean, I just got curious about Pratt parsing. We don't actually need it. We can just stick with recursive descent. In fact, I'm going to stick with recursive descent, but I just wanted to build this again to remember how it worked. Just making it pretty. Don't mind me. Okay, make sure that compiles. Okay, so we have the array of all the rules that we want to generate for a given token. All the tokens have indices. You know how enumerators work in C. The first enumerator has a value of 0, 1, 2, 3, 4, 5, 6, 7, on and on and on and on. And so we can reference like rules 1 and get like the integer token. The same way we would do this. Like we have a specific token that we want to find the rule for, so we index into rules using that token, and you see it matches. So we're going to have, we'll just call it Pratt for now, to differentiate it from the other functions. So we'll call it Pratt binary. This will need to take an expression. We just we're gonna forward declare it. Yeah, okay, so Pratt binary, unary. That's a prefix, so it doesn't need anything. What else? Unary, binary, primary. This is going to be a prefix as well. It doesn't take anything. And we can do grouping, which is primary. It's another prefix. So just to make it clear for you, token index, go here, this is the prefix, infix, precedence type. So again, I have it linked in the description, but we're referencing chapter 17 from the wonderful book Crafting Interpreters, where he shows you how to do all this. The only difference is that he's using a virtual machine and emitting the bytecode directly, but we want to have better debug capabilities, so we're doing it slightly differently, where every function is returning an expression instead of just returning void. And you can get a better idea of going through it on your own. I'm just going to blast through it to give you a basic idea of how to set up the code on your own without a, like, kind of a visual aid, if you will. But we're going to keep it really simple. We're just going to implement the mathematical functions. We're just going to do plus and minus and then leave it there. I don't got much time. So none will remain none. We're going to, for token number, we'll call this precedent primary. And for the prefix, we will call it Pratt primary, or Pratt number. Yeah, I think that's it. Yeah. Just call it Pratt number. And this will just return a specific number expression. Pratt number. Let's make it pretty. Oops. Pratt number, and then plus, minus, slash, those are all the terms. Plus and minus are going to be term, precedent term. Slash and star are going to be precedent factor. And minus will have Pratt unary prefix. Oops, that's the wrong one. Then plus, minus, slash, star. These are all binary expressions. They'll have an infix. You read the first character, that's like the prefix, so you read the number 1, and then you advance to the middle of the expression, and you can find a plus symbol or a minus or some mathematical expression. That's the infix in the expression. And so we're going to say Pratt binary. And doing something wrong. Unresolved external symbol Pratt binary. Pratt unary. Pratt number. Why is that? That should be right. Are we already getting slowed down here? I think we are. It must be pretty. Unresolved external symbol Pratt binary. Why is that? We define it up here. Must have misspelled it. Nope. It's correctly spelled. Wow. We got the token type. We got the function for prefix and infix. What happens if I just do null? Okay. Success. What's wrong with Pratt unary? Interesting. Well, I got it working a minute ago. I'll just reference the other code. I'm doing something wrong. I'm doing something stupid, but I just don't know what. Unresolved external. I think we're getting filtered here, folks. Well, let's try. It's prefix, that's the infix. Precedence type. Is it because it's not defined? Is that it? Is it just because those are only... Those are forward declarations. So you can't just append it to it. You can't insert a forward declaration into an array, is that it? Let's find out. Pratt number, and then return null. And then we'll enter that for the number token. Okay, that's it. Yeah. Okay, so you can't just use a forward declaration because that'll give you an error. You also need to actually define it somewhere. That was the problem this whole time. Imagine that. Okay. Learn something new every day. I don't usually work with function pointers. Not yet, at least. So we'll add that back in because for binaries, you will see why we need to pass in an expression. It's for the left component. Remember, binaries have left and right expressions, and then an operator in between to tell us what to do with them. And for that left expression, we need to pass in something. And in fact, I will just pass in left. That'll make a lot more sense, won't it? And I guess we can call it left as well. Why not? Okay, so that's for number. Then for the minus, we'll do Pratt, unary, all the same stuff. Pratt binary. And now we need to define them. Let's keep it all as null, and then it'll bite us in the ass later because we'll forget to set it. Binary, unary. Getting a warnaring. There we go. Let's just return. Well, of course, we'll need to generate a new one, so why not? We'll do expressions plus expression count, and we will return E, and we'll just assume that we do that for all of these. Oh my god. Okay. Look at that. Building successfully. So we have the basic array set up. We have the forward declarations. We have the precedence. So we can start with the Pratt expression, which will take nothing, and then we will call from here Pratt parse precedence. And then this will take a precedence type. And for Pratt expression, expressions will start. Remember, you have expression, and then it can break down into assignment. So we'll start there. We'll pass in. We'll return Pratt parse precedence. And then we'll pass in prec assign. We're getting a warning. Why are we getting a warning? Pratt parse precedence must return a value. Let's return null. Okay. So the end goal, the minimum thing that I want to get working today is we'll just do the same thing, print expression. We'll do Pratt expression. We'll do E equals that. We'll reset. We will reset the string count because we want to print it out. That's all we're going to do. We're just going to compare the printouts, and if they're the same, that means that we did something right. Pratt parse expression, and then we're going to print that expression. And then set that string count again. Okay. And then next token equals 0 as well, because we're going to be using all the same stuff for it, including, why not, expression count as well. So, of course, this is all temporary. Testing to compare against recursive descent. Again, I think long term, or at least until we're confident that we can generate accurate bytecode for the VM, we're going to stick with recursive descent. But I got curious and I wanted to remember how Pratt parsing worked. And it's almost the same thing, but instead you just read from a table, and you don't need so many functions, but you know, you still end up with quite a few functions. So I guess I can set a pointer in here for when we first enter. But now we're going to read through the tokens again. So we'll do token T equals tokens, next token. Remember, we reset next token. And using that, we have the token type, so we can get parse rule. Rule equals, I guess we can just access it directly. T.type. Then, now since it's an array, we want to pass a pointer to that rule. Okay. In crafting interpreters, there's a function like parse rule, get rule, and you pass in the token type, and then you just return rules type, right? the same thing again. That's what you do, right? But you can just do the same thing without calling the function. But since we have that set up, why not? Get rule t.type. Token type. Okay. So now we're going to get the rule for that, and we are going to check. The beginning of expression is always going to have an infix, like it's going to be an opening parentheses, or it's going to be a number value. And you need to make sure that when you're constructing this table, that you're going to need to assign a prefix function pointer to it. And we can do the same for grouping. Why not? Let's make a grouping one. I don't think, will we go that far? I guess we'll find out. But grouping would be another instance of having a prefix. So we can do left curly will be Pratt grouping as a prefix. And it must be perfect. It must be well spaced. It must be pretty. There we go. Okay, and error. Look at that. That is because we left this if statement empty. So it has to have a prefix value. So we can say rule, if rule, prefix, if it's null, if it hasn't been assigned, we can say printf error expected expression. I don't know. We can figure out the errors once we're further along, but right now we just want to make sure we can run the basics without errors, and we can do processing error ++ and return. Why not? Okay. Otherwise, we're going to do expression e equals rule prefix. This is a function pointer, remember, and it's going to return an expression. So in this case, like imagine that the first token is a number token, like it's the token 1. And so you go into get rule, you pass in the token number, and then you'll look it up here, and the prefix will return a function pointer to Pratt number, which generates, we can do that right now actually. So we'll do token t equals tokens next token ++, and then we can create a new expression, set the type to expression primary, e data primary, t equals t, and then return that expression. That should be good. And in fact, let's just see if we can do that. We'll just type in 1 for the program and see if we can get 1 back. 1. Okay, cool. So you see right here, let me just add another printf to make it clear what's happening. So we can do recurse, and then we can do Pratt. Type in 1. So you see for recursive descent we have 1, and for Pratt parsing we also have 1. So they look rather similar. Also, to make it easy so I don't because I run it, I need to click into the console and then I need to type something every time, but we can just add a quick little thing for sending in the same debug code every single time we run this. And so, I turned loop off, but it won't compile because we also need to do if loop, then we continue, else we're going to return. And if we're just going to run the loop once, or we're not going to loop at all in this case. Then I can swap these out. And then I also want to vary it depending on if we're looping or not. And so we're going to push these up. If we're looping, then we're going to keep prompting the user for input. Otherwise, we're just going to create char test string. Let's give it it could be tiny for now, and at 256 equals 1 + 1, right? That'll be the test string that we're going to feed in to parser test string. Okay. Let's just keep it 1 for now and see what happens. We'll run it. And so immediately I just press run, and then you see we get the output right away. We don't need a loop or enter our input or anything. We're just setting up a different path depending on the precompile definition, the preprocessor definition. So now we're going to test with 1 plus 1. So we're going to have a token number plus, token number, token plus, and token number. So we're going to have a prefix for number, we're going to have an infix for binary, and then that'll recursively step down and find a number, pop back up. We'll have the left and right for the binary expression and return that as part of a node and an AST. And so we need to flesh out the rest of this. So you have the prefix rule, and then as you go deeper and deeper recursively, you're going to want to, while the precedent is less than or equal, so like you call assignment, and so you're going to keep checking for every layer down you go, you're going to keep incrementing the precedence until you finally hit a primary value or it collapses into something, and then you hit a token that returns precedent none. And so, you know, like we call this with at minimum precedent assign, precedent none will be less than that. So as soon as you have that case, we'll stop recursively descending and we'll pop all the way back up. And so to do that, we do get rule for the next token. Oops, I want to use parentheses. Tokens, next token, precedence, get rule tokens, we need to just dot type. And then inside here, what do we do? Let's do another parse rule. Parse rule infix equals get rule tokens, next token, dot type. We'll just do that same thing again. And then we'll call infix. Oh, that's kind of nasty. And then we'll pass it what we already got. And then do e equals, we'll pass it, I guess we can just do left, or no, in case we don't hit anything. This will be the left expression. I guess, yeah, why not? Left equals e, then we can do left, yeah, and then we can do, that will increment the token, and then we can just return e there. Pretty sure that should work. So this will handle the plus token. And so we need to figure that out. So here in Pratt binary is where we'll do it. We can do, how do we do this again? We need to handle the left. We'll need to set the type. E type equals expression binary. E data binary. Left equals left. Operator equals token. We'll need to get the token. Tokens. Well, increment the token right here. Next token plus plus. T. And then we will do e data binary dot write. We need to call Pratt parse precedence again. And this time we'll need to get the rule for that token plus 1. We'll increment the precedence as we go deeper and deeper. I'm not doing something right. We'll need to do precedence. Getting the next rule, and we're just getting the precedence pointer for it. And not doing it right, of course. Wow. Must point to a structure union. We can get back a pointer. Let's just see what happens. Parse rule equals get rule. Do that type. Let's just do that. Comment that out. Parse rule differs in level of indirection from int. That's because we have it right up here, and we need to put it right below the rules. So I think this should actually work now. No, it doesn't. Rule. Precedence. Return expression differs level of indirection from int. That's because we also have Pratt Parser precedence right here. And I guess we could also move that up. Yes. Look at that. Okay. Cool. Yeah, so I think binary is completed. We're filling out the left, the operator, and the right. Okay. Let's just, I guess we'll just see what happens, whatever. Okay, that's better. We're not crashing, but we're also not going that deep. So now we'll step into it. And let's just step into it right here. Okay. So we're parsing the expression. Next token is 0. That's going to give us, man, this is really fast. I usually need to wait longer for the mouse hover to actually show anything. Why is that happening now? That's pretty nice. Okay, so anyway, the token that we get back is a number. It's going to be integer 1. And so we're going to go to the prefix for that. And you can see that we advance to the next token. We assign it to this expression. We're going to have an expression type primary whose data will contain that token of integer 1. And we return that. And then we passed in precedent assignment. We're going to check what the next token is. That's going to be a plus symbol. And it's going to have a precedence of token plus, let me find it, a precedence of term, which is higher. Assignment is going to be less than or equal to precedence assignment. So we're going to step into this. We're going to get the rule for that token, which will give us token plus. There's no prefix, but we'll have Pratt binary. And then we pass that in. It'll advance the token. We're going to have the plus symbol. We're going to create a new expression. Assign left, assign the operator. We're going to get the rule for the, oh, that's because, no, it's still going to be the plus symbol. Yeah, and then we step into this. We step into Pratt Parse again, this time with a precedence of factor, because we're only going to keep stepping up in the precedence list as we go deeper in recursion. We're going to get the next token, which is going to be a 1, and the precedence for, and so we increment the token there. So we're finally at end of file, which is going to have a precedence of none. Precedence of none is less than precedence of factor, so we'll return the expression from there, which is going to set the right expression in this tree to 1. Return it. We stop because next token has a precedence of none, which is less than precedence of term. We're going to check what E is. It's still, E.type is primary. Is that because we never set binary expression? E-type binary. We did set it, so why is it 1? That's weird. Let's try this again. Just step through it again. So E is primary. Infix, infix. What are we returning here? E is going to have a type of primary. We set the type right here. Am I doing something wrong? What happens right here? Am I crazy? E-type is binary. Where does it get reset? It gets reset in primary. Pratt Parser precedence. Okay, let's step into that. I don't see how that's possible. Step down here. E is primary. That makes no sense to me. Oh, that's because, yes. That does make sense. I forgot the plus plus. We're not incrementing the count, so we're just rewriting. Because we're drawing from an arena, we never incremented the count in that arena, so we just keep pointing E at that same slot that we're drawing from and overriding it every time we call a different Pratt parsing function. So, very easy mistake to make. You just got to remember to increment. That essentially means we're corrupting that slot in memory. So now, yeah, 1 plus 1, 1 plus 1, cool. So you see, recursive, we get 1 plus 1. Pratt, we get 1 plus 1. We're overriding that expression for when we evaluate it, and we still get the same thing, so it's still 1 plus 1 equals 2. So we made another basic calculator with Pratt parsing instead. Let's do 2 plus 2 plus 1. That'll be 5. Why is this different now? Oh. Because we're not actually calling it. Let's call loop instead, so we can give it some actual test values. Let's do 1 plus 1 plus 2. That'll be 4. They both evaluate to the same thing, recursive and Pratt. That's cool. So now let's, we got a little bit more time. We could add a few more rules, but you see that already we have Pratt parsing, the skeleton of Pratt parsing figured out. You just need some enumerators. You need the struct for the parsing rules. You need to forward declare some functions. You make a big array of all the different rules you would want. Get rule, Pratt parsidence, Pratt parse precedence, Pratt parsidence, then all the different functions, and then finally you start it with Pratt expression, which gives it like the base precedence that you then increment from. So I guess we could, why not? Let's, I think this should handle multiplication, division. Like, let's see what happens when we do 1 minus 1. Okay, 0, cool. 1 times 2, 2 times 3. Okay. Yeah, wow. So that, yeah, we already wrote all the object handling rules, like, because we just pass in this expression. We still generate the same abstract syntax tree with the Pratt expression, and we evaluate it with that same code that we made yesterday. And now I guess I'll just do grouping. And so for grouping, you're going to want to call Pratt expression again. So you can do E equals, you won't allocate anything here. You'll just do E equals Pratt expression. And then, am I doing this right? Am I thinking about this right? Probably not. Pratt expression. Pratt precedence. Move it up here. Can't compile when it's running. Okay. So when you have a grouping, I need to look up expression grouping. So we're going to want to make a grouping type, and then we'll set a pointer. So yes, I think in this case for grouping, we do want to allocate another expression. Set the type to expression grouping. Oops. equals expression grouping. And then we'll do e dot data dot grouping dot e equals Pratt expression. And this should allow us, you need to add a rule for it. So left parentheses, oh, I did it wrong. You need to put that Pratt grouping right there. Curly braces are for encapsulation. We can get to that later if we ever do. And then precedence will be a sign because we're just starting over from there. And let's see if we can do 1 plus 1. Okay, well, that didn't work. Expected expression for left parentheses. Oh, and then if it's a right expression, yes, for Pratt, we got to increment the token, and then we also need to check if tokens next token dot type, I guess we don't need to do plus, equals token right parentheses. Oh god, what did I do? If it doesn't equal, then we get an error. Oh god. Oh god. If it doesn't equal, you get a processing error. Printf expected closing parentheses. And then we return, yeah, why not? We'll just return an error, and then we'll do next token plus plus. I guess we can do that right there. Let's see what happens down. Whoa, that's crazy. Okay, so yeah, it works now. So I guess in 40 minutes we already set up everything that we had yesterday. Of course, we already have the object and the evaluation working, where we go through, we recursively step through the abstract syntax tree to generate all the values. In the chapter of crafting interpreters, chapter 17, I think this is from, he emits bytecode directly for the virtual machine. Again, we're not going to worry about that. We're just generating the abstract syntax tree. This is another method to do it. Eventually, we could generate the bytecode ourselves in this, but it'll be easier for us to debug if we just step through the abstract syntax tree for the next few days. And I just want to test 2 times 2, 2 minus 2 times, I don't know, 3 times 3. Let's see what that does. Let's make sure they're both the same. Yep, and what will that evaluate to? That'll be 9, 18, 2 minus 18 is negative 16. Then you see that it looks like it works for both recursive descent and Pratt parsing. So that's how you do Pratt parsing. So far we only have, I guess we could also add unary. Yeah, why not? We'll add unary. So just one more rule. Yeah, I guess we can do that. We can do type expression unary, the operator e data unary operator is going to equal tokens next token plus plus. Do e data unary e is going to be parse Pratt parse precedence. And we're going to give it, we already know that we're in unary, so I guess we could just do plus 1. Then what date is contained? Right. It's not e, it's right. Yeah. Okay. And so now we can probably do -2. Just test, yeah, -2. Okay, cool. Yeah, so it's in some cases easier to set up once you have all the rules, because you're not doing recursive descent so deeply like we did yesterday. So, I mean, there's trade-offs for everything, of course, if you have difficulty. I mean, it's good practice if you don't really know anything about function pointers or dealing with structs of arrays. No, sorry, arrays of structs, then it's good practice. It's just another method to generate an abstract syntax tree, so I mean, of course, I kind of blazed through it. Yo, Yahia Ladev. Yo, good luck. I'm learning it too. Just learning Shantan yard algorithm for a calculator now. I want to make it typed-like language. Thank you. I really needed an experienced developer ideas about how to approach stuff like this and see. Thank you. Well, I guess I'm experienced, but I'm really just basing it off of crafting interpreters. I just reviewed the contents today and got it working and figured I would stream it. But you can read chapter 17. I think it's linked in the description, and it'll show you how to do all this. He does it a bit differently. Like, you'll see that he does, I think in his binary equation, you see that he's not returning anything. He returns void. But because we want to take an abstract syntax tree out of it, we're returning all the expressions back up. So we're doing it slightly differently. We're not emitting bytecode either. Because, yeah, and the operator type, so he checks what it is, and then depending on what the operator is, he emits bytecode for it. So we're just doing it kind of differently. But yeah, this is just one way to do it. It's good. A good experience for learning a language. Where do we go from here? Because we basically got everything. Let me make sure that we can do -2 times 2, right? That'll be 4. Cool, 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 cool. Okay, so about -2 divided by 2. How about that, huh? What if we do times 0? That'll crash us. Or, sorry, divided by 0. Yeah. Okay, that's because we're dividing by 0. We don't have a check for that. We can do if O2 data integer equals 0. We do tuck that into a little else statement. Or we don't even need an else statement. We'll just return right there. We can printf error dividing by 0 and do runtime error ++ and return 0. Why not? Cool. Okay. Now let's try to run that again. Let's see what happens. Oh, damn. Okay. O is null pointer. Oh, that's because we're returning an object? Yeah. Okay. So, I guess we could just return. It doesn't really matter. We return O there. So, I guess. Yeah. We'll just set O data integer equal to 0 and return O. Yeah. Cool. Okay. Let's just run it. Yeah, there you go. Okay, so that's how you need to handle all the math operations when you're writing the language, so you're going to need to handle runtime errors. This is just one way to do it. Of course, crafting interpreters teaches you how to store the exact line that you got the instruction from so you can return more information. We can add that later when we actually need it. We're being very pragmatic here, learning the little pieces that we want. And I think what I would want next is assignment. Like, I want to set the minimum viable product, if you will. Plan. Get working. I'll have int x + 1 or int x equals 1, int y equals 1, and then we want to do int z equals x + y, right? That's basically what we want to do. So we're going to need requires statements, declaration statements, where you declare a variable, assignment, assignment, and I guess that's it, because we can add numbers together. So we just need to, the next step is where we can declare variables, store them in that hash table that we made on day 1, and from there, I mean, it's just more math. But that's what the next step, once we have that, is to break it down into VM text commands, where you would do for x. I'm not sure how you would do this. I'm going to learn how, and then we'll implement it on stream once I have a basic understanding of it. So it might take a few days until I stream again. But I said that yesterday. But we'll do mov into register 0, the value of 1, or whatever x has. Move to register 1, the value of 1, whatever y has. In assembly, you use the semicolon for a comment. Y equals 1, X equals 1, and then you'll do mov, or sorry, you'll do add. You'll add register 1 to register 0, X plus Y, and then we'll need to store that somewhere. So I don't know how to get that far. That's what I'm going to figure out in the coming weekend. But we have the basic higher level language where we can do math, and we have the lower level back end virtual machine that I wrote. All I care about right now is connecting the two together and using what we've written so far to generate simple text assembly instructions like that. But that's the long-term goal. We'll get long-term plan. But so far today, we just demonstrated how to implement Pratt parsing. I don't know if we're going to use it long term. Like, I can just pull it out now. That was just to demonstrate how you set something like that up, and you can build on that later. But I think for now, I'm just going to keep working on the abstract syntax tree with recursive descent. So we can just do if 0, just comment all this out. We do and if. That's cool. That's some new feature of VS Code. Okay. And now, let's just run it. We'll do 1 plus 1 times 0. We'll get 0. And the recursive descent returns that abstract syntax tree, and we evaluate it, and we don't send it through the Pratt parser. So we just disabled all that code we wrote, and we're sitting at 1,000 lines. That's crazy. That's just a drop in the bucket. So again, just a little cursory stream demonstrating some material from a book if you want to learn more about language programming. It's just like an audio-visual aid for how to set something like that up. And then using this and the book, you can generate more rules. But this was just a little overhead explanation of how to do it. If you want to return values to make an abstract syntax tree, again, he's generating the bytecode directly. So there's a few differences, but really it's all the same. So that's all I wanted to cover. I'm pretty tired, so I don't think I'll stream for the 2 hours like I usually do. So thanks for watching. If you have any questions, just leave any comments. The repository is linked in the description, so you can see this code too and play around with it. There's everything you need so far. So thank you so much for tuning in, people, and